Very well, good morning. Today we're going to close the first section of our energy management lectures by taking a look at a case study that is the Toyota Prius, which, as everyone I think understands, is the first hybrid electric vehicle to be introduced in the market commercially. Toyota introduced the Prius in Japan, I think in 1997 or 1998, and it came in the US in model year 99, which really means in early 2000. So it's a vehicle that has gone through many different iterations, and I will mostly today talk about the second generation Prius, but I will make a comparison with the first generation Prius as well. By now, millions of vehicles with this type of powertrain have been produced commercially, and it's been quite a success in the sense that they continue to be sold, and there really haven't been, one of the initial questions was what happens to the battery in a hybrid electric vehicle, and it turns out that the Toyota Prius battery has demonstrated that it has plenty of life consistent with the rest of the vehicle. So let's talk about the configuration, or rather the different, the two generations of Toyota Prius. So from 1997 to 2003, sorry, I forgot to enable editing. Okay, now we have it. So the first generation was introduced, as I said, in 1997 and sold until 2003. That vehicle had some initial success. It certainly sold a number of units, but when the Toyota Prius explosion really began was with the second generation that was marketed in 2004, and I will explain that difference. By now we're in the fourth generation, but the changes that have occurred since the second generation are relatively minor. There are obviously improvements, but the basic operation is the same. So I talked already, when I talked about planetary gear sets, I did talk about electrically variable transmissions, and today we're going to go into more detail. But this picture will refresh your memory as to what happens in a hybrid configuration that uses a planetary gear set. And the way it works, just a small adjustment here. The way it works is that you have the engine connected with a through shaft to the planetary carrier. So that's the carrier, and that's what the engine is connected to. Then the generator, it's an electric machine that operates as a generator much of the time, but it can also operate as a motor. That one is connected to the sun. So the sun is the middle of the gear set here, and so this would be the generator. And you can see that this picture here shows you the rotor, which is this portion, and the stator, which is that portion. Finally, the carrier, the ring gear, which is on the outside of the planetary gear set, is what is connected to a motor, again, another motor generator that operates more often than not as an electric motor, and that is in turn also connected to the final drive, so to the differential and to the wheels. Okay. So the relationship that you have between the output shaft, which is the ring gear, so that's in green, and the sun and the carrier is given by the relationship that you have for a gear set based on, for a planetary gear set based on the number of teeth that you have in the sun and ring gear. So you see that these relationships are fixed. So you say, if the relationships are fixed, how do I make this into a continuously variable transmission? You do it by varying the velocity of the MG1 which is the machine that is on the, let me use the correct color, that was blue. So by varying the velocity of that machine, I can effectively change the speed ratio between the engine shaft and the output shaft. And what is especially attractive about an electrically variable transmission as opposed to a continuously variable transmission of a mechanical hydraulic type is that in this electromechanical configuration, I am able to achieve speed ratios that are of as wide as 10-to-1. A mechanical CVT or a hydrostatic CVT, if you're familiar with hydraulic systems, will typically give you a speed ratio of about 5-to-1, 6-to-1. So one of the great advantages of this configuration is that you can get a continuously variable transmission between engine and output drive, transmission output shaft, that is as wide as 10-to-1, which improves the opportunities to optimize the engine operating condition. So here is the picture. Of course, the colors are different than the ones I used before, but it doesn't matter. So you can see here again in more detail that the engine is connected to the carrier. The electric motor generator MG1 is connected to the sun, and the output shaft goes to also an electric motor generator too. So approximately you would have a smaller, I'm not sure that 10 kilowatts is the exact power, but we will come back to that in a minute. I think it's more than that, but there is a smaller electric motor generator, a larger electric machine, in that case 50 kilowatts I think is the correct number for the Toyota hybrid system too, and then you have a carrier that is connected to the 1.5 liter engine. By the way, bring back memories of my lecture on internal combustion engines. Toyota also understood very clearly that they could not only improve the efficiency of the engine operation by having this wide range continuously variable transmission, but also they realized that because the electric machines give you excellent torque at low speed down to zero speed, you could afford to use a combustion cycle in the engine that would be somewhat underperforming in a conventional vehicle, that is the Atkinson cycle. The Atkinson cycle has lower IMEPs, lower torque, but it gives you better fuel economy. And so the combination of an Atkinson cycle engine, which by itself would not be very good, and the electric drives that help assist that engine in providing torque makes for a really effective design configuration. It turns out that years later, a few years later, when Ford introduced its own hybrid electric vehicle, the first one they did, which was the Escape, they decided to license some aspects of this configuration from Aisin Seiki, which is the company that produces the EVT from Toyota, because they recognized after doing years of studies that it was difficult to do much better than that. And so if you want to find information online, you can. I have lots of pictures here. This is a slightly more involved description of the system that shows you that, first of all, the engine is connected to a transaxle damper for NVH quality, that the actual gearing includes some counter gears. There are systems that are organized, that are arranged to balance torque and power, connected via silent chain. Of course, you also have to operate an oil pump, which is on the output shaft where the MG2 is. So this is a slightly more detailed configuration of the system. I'll show you some pictures. The other thing that was quite innovative about the Toyota Prius was the integration of all these elements into a very neat package. Because when you look at the package here, it looks a lot like an engine connected to a transmission. Inside the transmission, however, you're going to have MG1 if you look carefully, this is the stator of an electric machine, okay? And you can see that sorry, oops, I better get the terminology right. That's MG2, okay? MG2, which is the one that is connected to the output shaft that goes to the differential. And this smaller machine is MG1, the one that is connected to the sun. You can see the silent chain here and the counter gears. From a configuration perspective, if you open the hood of the Toyota Prius and take a look at the configuration, it looks just like a standard transaxle. It would not be, from an outside top view, it wouldn't look much different than a small transaxle with a four-cylinder engine and a small automatic transmission. I repeat my invitation. If you're really interested in this, we have an old Toyota Prius, I think it's a 2010 model, and you're welcome to come to car, open the hood, get the keys, drive it. The only thing that I ask is that if someone drives it, you better be registered with Darren. The EcoCar team knows how that works because it's an official OSU vehicle. But anyways, please do that. I really invite you to do it. Here is a similar picture in which you actually now can see that these gears have been cut out. So you can see that the MG2 here has been sliced, so you can see the interior. And what you can see here, and this is MG1, you can see here that you have windings. You'll see copper there. So this is the rotor inside, and this is the stator outside. And again, you can see the silent chain that I was talking about. So the MG1 operates as a control element. So it's important to understand that this first electric machine is the control element for the planetary gear set that splits the power. And when it acts as a generator, it recharges the high voltage battery, and it also supplies electrical power to drive motor generator 2. So effectively, I've already said this, but I want to underline it, MG1 controls the continuously variable transmission function. That's what it does. By changing its speed, we can change the effective speed ratio, speed reduction ratio. In addition to that, since it is very close to the engine, sun to carrier to planet gears, it also serves as the starter for the engine. MG2, on the other hand, it's right on the output, okay? It's connected by a differential gear to the output shafts, and so basically it is the primary source of motive force at low speeds. One of the things that you will notice if and when you drive the Prius is that at low speeds and launch, the vehicle feels and is an electric vehicle. The engine doesn't need to turn on. It also provides supplemental torque at high speed. It can assist the engine output as needed. So it provides that hybrid torque assist. It also provides the regenerative braking function, which, since the Toyota Prius is a front-wheel drive vehicle, allows you to, and this motor is right at differential, basically, you're able to maximize the recovery of braking energy. You don't get any from the rear wheels, of course, but at least you have it on the front wheels. So here are some numbers that are important and need to be considered. By the way, this lecture, I'm hoping, forces you to remember a lot of the things that we talked about when we spoke about internal combustion engines, electric machines, and power converters, because all of these topics are going to come back. So hopefully you remember some of the details I talked about in these different earlier lectures. So let's talk about the difference between the MG1 specifications, first of all. So I'll make, there is no difference between the 2003 and 2004 models. It's a permanent magnet synchronous machine. We talked about permanent magnet synchronous machines. It's used as generator and engine starter. If needed under extreme acceleration, it can provide positive torque as a motor as well. Here is a really big difference that the system in the 2003 model operated on a 270 volt bus system, whereas the maximum voltage in the 2004 model is 500 volts. Remember that increasing the voltage in any electrical system will result for equal power in a reduction in current. So that means that if I reduce current, the benefit that I have in terms of reduction of power losses, I squared R, ohmic losses, is actually squared. So increasing the voltage in general is a good idea. Let's look at MG2 because the changes in this are more significant. So you have, again, an increase in voltage, but Toyota went from a 33 kilowatt to a 50 kilowatt electric machine, and from a maximum torque of 350 to a maximum torque of 400. And the way this, I don't remember if I talked about this, but the way the torque increase is achieved is by changing the configuration of the interior permanent magnet. I think I have mentioned this, but let me just sketch two quick pictures. In 2003, the interior permanent magnets in the Toyota Prius were slabs of rare earth materials that were incorporated into the system with that geometry. In 2004, the design of the machine was changed to provide some reluctance torque. So you'll see that instead of a continuous slab, these elements are placed in a V configuration, and this V configuration allows you to produce some reluctance torque in addition to the permanent magnet torque that increases the peak torque you can obtain from the machine. So, of course, you know that the connection between the machines and the engines is done by a planetary gear set. One of the other great advantages of this configuration is that Toyota decided that simplicity, which also means lower cost, was a great benefit. Therefore, they utilized a single stage planetary gear set. And you may remember that when I talked about EVTs, I showed you, for example, the GM two-mode hybrid system and the Chevrolet Volt hybrid system, both of which actually have two-stage planetary gear sets. And having two-stage planetary gear sets may require the use of clutches. There are no clutches or band brakes in the Toyota Prius second generation. So if you're curious about the numbers, remember that there are this N sub R, the number of teeth in the ring gear, N sub C, the number of teeth in the carrier pinion gears, and then the sun. You can see that those specifications are given here. And then there are some additional pieces of information. For example, while the planetary gear set gear ratios are the same between 2003 and 2004, the final drive is slightly changed, and it was possible to go from 3.9 to 4.1. In general, increasing the ratio of the final drive is good for fuel economy, but do you have enough torque to do it? If you don't have enough torque, the vehicle might lug. Well, with the increase in torque and power, it became possible to increase the final drive ratio. So there is a chain of events which are all positive and favorable with respect to fuel economy. The inverter, of course, we talked about the inverter as being fundamentally something that converts DC power to three-phase AC power. And the battery, here is a very important element. The battery changed dramatically. In terms of the modules, they were nickel metal hydride modules, excuse me, each of which has 6 cells in it. They're about this big. For those of you who happen to wander by my office sometime, say, may I please see a Prius 2004 battery module, and I will show it to you. I have it on my shelf. It's kind of a piece of history. The reason it's a piece of history for us is because in 2004, we used the equivalent of 16 Toyota Prius batteries in our electric land speed record, the original Buckeye Bullet, to set the US land speed record. We did it with the equivalent of 16 Toyota Prius battery packs. So in 2004, they went to 28 from 38. So they went from a DC bus voltage of 273 volts to a total voltage of 202 volts approximately. You say, what do you mean? You just said 500 volts. Aha. What Toyota decided to do was to incorporate a DC to DC converter between the battery and the inverter so as to raise this voltage with a DC to DC conversion to nominally something like 500 volts. And you say, but a DC to DC converter, that's more power electronics, it's more losses. Yes, but the gain that you have in reducing the I squared R losses of the motor because your currents are lower are actually worth it. So you gain more by reducing resistive losses than you lose by incorporating another piece of electronics that in fact might have an efficiency of 95%. Okay. So that's what the battery pack looked like. And so let's talk a little bit about how things go. The inverter in the Toyota Prius, and here now we go back to the lecture that I had on power converters. I hope that you remember some of that. What you have here is a three-phase bridge. Not one. You have two three-phase bridges, right? Because one is for MG2 and one is for MG1. You need to have two independent inverters to power the two different electric machines. They're in the same package, but this configuration in which you have 6 switches, IGBTs, and of course you have a flywheel diode for every one of the IGBTs to take care of voltage transients. So those 6 switches in the top in blue are one inverter, and the ones in the green box are another inverter for MG2. I also want to point out a couple of things. Do you know what these symbols represent? You put a coil around the wire. Why would you do that? To measure the current, right? So you'll notice that there are 3 phases, A, B, C, in a 3-phase machine, but we only measure 2 currents. We measure only 2 currents because the third one, by definition, can be determined from the other 2. They are related by trigonometric relationships. So each of those inverters has 2 current sensors. And there is a boost converter here. This is a not so clearly understood function, but you have to realize that the input to the inverter can see DC voltage fluctuations that are significant. I say that the battery pack voltage is approximately 200 volts. By the way, if you want to know how you get to the battery pack voltage, let me give you the nominal battery pack voltage. So one nickel metal hydride cell is 1.2 volts. One module is equal to 1.2 times 6, which is 7.2 volts. One pack is equal to 28 times 7.2, okay? Everything is in series. So nominally, it's about 200 volts. But you know perfectly well, what does the voltage state of charge characteristic, so if the state of charge goes from 0 to 1 or 0 to 100%, what does the voltage do? Well, it starts at some maximum value and then it decreases, right? So is the battery pack voltage constant? It's not. As it changes in state of charge, the voltage will change. Therefore, this boost converter is something that the DC to DC converter also has the function of stabilizing the DC voltage for the system. If the DC to DC converter, if you look inside, what does that look like, is actually a rather complex element, because you're going to have some switches that allow you a transformer and an energy storage inductor. And I really have not had time in this class truly to talk about boost converters, but if you're interested in that, I can point you in the right direction. With the inverter we've really talked about already, but if you now go back and remember the block diagram of the inverter that I showed you, yes, you have IGBTs and protection diodes in the circuit, but you're going to also need a gate drive. Something has to switch these switches on and off, and the gate drive is in turn driven by a switching algorithm that is in some kind of a microcontroller. Okay, so remember that the operation of the inverter requires some fairly sophisticated algorithms. I don't think that this picture is very important. This is a very high-level set of control functions. This is not really that important. So the idea now is that, in effect, by having an electrically variable transmission that allows you to adjust continuously the speed ratio between the engine shaft and the output, the transmission output shaft, you're effectively reducing the engine operating range to a very narrow range of operation, depending on how much power you need. First of all, you are not going to use the engine much in the low torque region, because you have an electric machine that can do that for you. Second, when the engine is on, you're going to be able to arrange for the EBT speed ratio so that you are truly in the highest efficiency region of operation of the engine. So it's a CVT at its best. I will bypass this slide. This is much more interesting. So what about regenerative braking? Regenerative braking, as we've already discussed, is in principle a wonderful thing. It's essentially a gift of free energy, because you already had stored kinetic energy in the vehicle, and now you are recovering it. It was already stored in the vehicle, so any energy you can derive from it comes to you for free. So that's great. But you may also remember that it's limited by the power rating of the electric machine. So effectively, in the generation 1, I want to remind you that you have a 33 kilowatts electric machine. So the amount of power that you could recover from regenerative braking is limited to the maximum capabilities of that particular machine. So it's braking power was limited to 33 kilowatts. In the second generation machine, you have an expanded regenerative range, because in Gen 2, you have a 50 kilowatt electric machine. So that's another benefit of having been able to increase the size of MG2, because you also have the ability to recover more power. Now, this is not to scale, but of course, you need to point out that what if your braking power required to slow down the vehicle is greater? Well, at that point, you're going to have your friction brakes that are hydraulically actuated. What you see in this diagram also is that the philosophy that Toyota adopted for their braking system is what we call a series braking regeneration strategy, meaning that first, you get all of the electromechanical regeneration you can. You maximize the electromechanical regeneration, and then you resort to friction braking only when it's absolutely necessary. So what I'm going to do now is walk you through a series of pictures that are going to show you how the different modes of operation of the vehicle take place. So when the vehicle is stopped, nothing happens. Now, my car today also has an engine start-stop system, but back in 2000 or 1997, when the original Prius came out, the notion that the engine would stop whenever the vehicle stopped instead of idling was quite revolutionary, and that results, of course, in fuel savings. When you are starting out, launching, light load and light throttle. So if you do a test drive on our Prius, you should try the difference between a gentle start, in which case only MG2 will turn on. It'll be an electric launch. But if somehow you want to stomp on the accelerator pedal, then the engine will come on as well, because MG2 cannot provide enough power to sustain such a hard acceleration. So if you are trying to do drag racing at a traffic light on a Saturday night, then the engine will turn on. If you're driving sensibly, the launch will be electric. And MG1 does not generate electricity, does not do anything. Okay, it rotates backward. It has to do something because it's connected by a gearing system to MG2, but it doesn't generate any power. So every electric launch of this vehicle uses electricity that you'll somehow have to replenish later. Let's call normal driving, low-speed driving, 15 to 40 miles per hour. This is what would happen under most conditions as you're driving in an urban, suburban setting if you don't get on the freeway. At this point, you're going to have the engine as well as MG2 providing electric assist. Now, it's important to understand that MG1 now is also caused to turn by the engine, and it provides electricity for MG2. So what happens is whenever you use the engine, some of the engine power is going to be transmitted by the generator back to the electric DC bus through the converter, and it becomes available to provide power to the wheels. It's important to understand that because there are no clutches in this system, you can't forget about MG1. So the Toyota Prius system is constantly recirculating electric power, constantly. It's always once the engine is on, both MG2 and MG1 are operating, and MG1 is usually generating some power, which you can use to power the wheels. So you might say, gee, why do that? Because it seems that if you're continuously recirculating this power, there are losses, right? Nothing has a perfect energy conversion efficiency. And that's true. So one of the drawbacks of the Toyota Prius architecture is that if I am cruising, here it says low-speed driving, but this is true on the freeway as well. If I am cruising at 70 miles per hour, I'm actually recirculating electric power all the time, which you could argue that's not necessary. The engine would be good enough to give me 70 miles per hour operating at a very good efficiency. I don't need the hybrid system. But in order to make that happen, you would need a clutch or a band brake. You would need to be able to lock one of the elements of the transmission and to essentially treat the planetary gear set as a mechanical transmission. That is done in the GM two-mode hybrid and in the Chevy Volt, but Toyota chose to keep simplicity in its system, and it simplifies not only the mechanical construction of the system, but also the control. You don't have to worry about clutches, okay? And so that simplicity is paid for in terms of probably a little lower fuel economy on the highway than you could get. On the other hand, the fuel economy in the city is excellent, and so one of the characteristics of the window sticker of the Toyota Prius when it originally came out was that city fuel economy and highway fuel economy were virtually identical. Now, what if you do full throttle acceleration? Okay, well, if you have maximal acceleration or speeds over 100 miles per hour, which in Montana you can do, but not in Ohio, then MG2 is capable of supplementing electric power. Of course, what happens is that, well, several things happen. MG1, so you have MG2 providing power. MG1 also receives electrical power and turns in reverse direction to create an overdrive ratio for maximum speed. So whether you want to, if you want to reach maximum speed or have a really hard acceleration, now both MG1 and MG2 are providing positive power. Of course, now you are depleting the battery. So this is not a condition that can be sustained indefinitely. Under deceleration and braking, as soon as the driver releases the accelerator pedal, MG2 now turns into a generator. So somewhere in the control strategy, when the accelerator pedal position goes to 0, MG2 becomes a generator. This means that it's going to begin to recover kinetic energy immediately. Now, this is a matter of calibration for good driver feel. If in a conventional automobile you release the brake pedal, the vehicle will slow down. What causes the vehicle to slow down? Well, there are some unavoidable losses that have to do with the vehicle road load. Aerodynamic drag, you can't remove that unless you're in vacuum. Friction, rolling resistance of the tires. So the vehicle would naturally slow down. In an engine, there is something that we call compression braking, because the engine, when not powered, still needs to move the pistons and compress the air. So that compression braking, if you have a vehicle with a manual transmission and you don't touch the clutch, you will feel it a lot. In a vehicle with an automatic transmission, the torque converter, if it goes into fluid coupling mode, will make this compression braking less obvious. What Toyota did was to try to create, by appropriately calibrating the regeneration parameters, a situation in which when you let the accelerator pedal go, the engine can turn off. You don't need it anymore, so there is no compression braking. But that feel of compression braking is given to you by MG2 operating as a generator. So it's gentle, and if it's properly calibrated, you will not feel any difference than if driving a conventional vehicle. If some of you have driven an electric vehicle, for example, a Tesla, you may have noticed that when you release the accelerator pedal, you have to get used to it because there is a fair amount of regen braking. In some ways, the coasting braking, quote, compression braking effect in an electric car is often increased to the point that it doesn't feel natural to the driver, because in an electric vehicle, you want to always recover as much electrical power as you can. So people have to get used to that, by the way. It's not an immediate. So the regenerative braking process we just talked about, and the engine stops running. I said that already, and MG1 turns backwards and maintains whatever speed ratio is appropriate. In reverse, that's easy. Reverse in an electric drive system is incredibly easy to accomplish. All you have to do is change the direction of the field in the electric machine, and the machine will turn in reverse. So reverse is basically just an electronic switch in an electric driven vehicle. So the idea then, I think we've just kind of summarized all the different operating modes. And the overall control system diagram is this detail block diagram, which I won't worry about at the moment. You can take a good look at it. These are all from the Toyota hybrid system. What we're going to do now, having used a lot of words to explain these things, I am going to use some images to explain the different operating modes. So what we're going to do is to look at different regions of a possible operation of the vehicle, and we'll call this one ready on. You will remember that when we talked about planetary gear sets and automatic transmissions, I introduced a concept called the lever diagram, or lever analogy, in which we think of the gear ratios between sun, planet carrier, and ring gear as being, they're related by fixed relationships, and you can think of it as a lever. As the speed of the different gears changes, you'll be in different positions with this lever. Well, in this case, everything is at zero because nothing is happening. Okay. Now let's go on to the starting out. So then now we're going to look at the initial launch. The initial launch, we said, is going to be done in electric mode. So what's going to happen is that this blue arrow here means driving. We are driving the MG2 in a positive direction, so that's providing power and torque. MG1 is just doing nothing. It's spinning because it's mechanically connected to MG2, but it's not powered. So this is a charge depleting operation for a short period of time. Okay. And the engine, well, the engine is at zero speed because we haven't started the engine yet. So the speed at which MG1 rotates is determined by the speed of MG2, that's all. So, and this is, probably I should have had this picture before the previous one, but this was a quick refresher on how the lever diagram goes. So carrier, speed, ring gear speed, and sun gear, number of teeth versus RPM at the generator, at the motor, and at the engine. So you can see here this lever diagram. You have a question?
How is the engine speed set zero? How can there should be a clutch or some brakes that stops the engine from rotating?
You don't turn it on. So that becomes, the engine is not moving because we haven't started it yet. So that gear that is connected to the engine that is not moving is actually stationary. And the two gears rotate around it.
But the torque is being sent because motor is providing torque, so some torque will be at the engine shaft.
But it's not. So what happens is that the torque that the motor is providing is transmitted to the generator via that gear, but the gear is stationary. In a sense, the engine stopped is acting in some way like a clutch. I mean, it's a good question that you're asking, but when the engine is off, it's not moving, and its inertia, its mass, and is enough to keep the sun gear, the carrier fixed. So the carrier becomes a stationary reference, and all you have then is a clearly defined speed ratio between MG2 and MG1. Once I start rotating the engine as well, then there are now three variables, three speeds that come into play. Okay. And here is the relationship. So in this case, what happens is that the speed of the carrier in the example I just gave is zero, okay? And then the relationship between the ring gear, which is MG2, and the sun, which is MG1, is NS over NR, okay? So if you now increase the speed and we go to the second step, you'll see now that what's going to happen in the next step is that when the engine starts, its speed now is non-zero. What that does is to shift this diagram up. You see what we've done? We've shifted the entire diagram up because now the carrier speed is no longer zero, it's moved up, and so you're going to have the same relationships because this is the same, but now omega c is not zero anymore. So we've shifted the entire lever diagram. In fact, that's what I'm going to show you now in this diagram. We'll go into light acceleration with the engine. So let's suppose that we have done what we needed to do to launch the vehicle, and we've reached a point where we say, no, I'm not going to use any more state of charge. Let's turn things on. So what's going to happen now is that I'm going to have two elements that are driving both the engine and MG2 are accelerating the vehicle. That changes the relationship with respect to MG1, which now is driven. And this time, this is turned on. There is an arrow there. Remember that here in this initial launch, this was not powered, okay? There was no arrow there, there's no power. Now, what I'm going to do is I'm actually going to provide power to it. But when I turn on the electric machine MG1, it is being powered as a generator. So it's producing electricity, which can do two things. It can charge the battery, or it can go back on the DC bus and provide power to the wheel if necessary. So that's the light acceleration with the engine. And what is happening now is that, of course, all of this needs to happen as a function of what the battery state of charge is. So the extent to which you can launch the vehicle electrically is dependent on what your state of charge is. If somehow, let's imagine that you just came down a big hill, okay, and you were coasting and braking to come to a stop, and the traffic light is at the bottom of the hill. What have you just done? You have probably charged the battery as much as you can. You know, you've recovered as much kinetic energy as you can. The state of charge that you're going to have now when you're at the bottom of the hill and the light becomes green is, let's do a really nice electric launch. I just got a lot of free energy, and so you may be able to get up to a higher speed and have longer electric launch. Eventually, the engine will turn on when the state of charge comes back down. So this information about the state of charge is very important. There isn't a fixed strategy such as I am going to launch electrically for 15 seconds every time. It depends on what your state of charge is. It could be, let's reverse the example. I just came up on top of a really big hill and I used a lot of electric assist to get me to the top of the hill, and then the red light now is at the top of the hill. Maybe my state of charge is really low. It's possible that I may not even be able to do an electric launch. I may need the engine right away. Okay. So then, after having coasted for a little while, I am now going to go to a full acceleration. And in this full acceleration, this is actually similar behavior because I'm going to drive both the engine and MG2. I'll just simply require more power of them to accelerate harder. And again, the MG1 is going to be driven. So I am, again, recirculating electrical power. And so what's going to happen here is that, let me see, what does this say? Well, it is also possible that in the case of a hard acceleration, there you go, that's the case. Well, this is the max speed case, but it'll work in a really hard acceleration as well. So now, for some reason I wish to drive at the maximum speed. I have personally never driven a Toyota Prius over 85 miles per hour, but I think it can. I have never tried because even 85 is a stretch, but maybe there's a long access ramp to the freeway on I-670 from Dublin Road from 33, which is long enough that you can actually try something like this out without doing anything that is overly dangerous, because mostly there are no cars on that stretch. So I have taken a Toyota Prius 285 on that stretch. Never tried any more than that, but it does that pretty comfortably. And what happens now is if you have a hard acceleration is this time you're going to, everything is going to actually drive. So in this case, notice that I went from green to blue because MG1 now is acting like a motor, not like a generator. And in deceleration and braking, what's going to happen now, here's another important point. So take a look at this. This is now braking and deceleration, okay? Point number one, I turn the engine off. That speed is 0. Now that the engine is off, the relationship between MG1 and MG2 is fixed by that ratio of ring gear to sun gear speed ratio, because the carrier is not moving. So I have a single speed ratio. And look at what happens. The MG2 now is driven, but it's driven backwards. this direction has changed backwards, which means that it's actually regenerating power, and MG1 is doing nothing, because all I want to do is, so it's just spinning, idling, without any power flowing through it. Now, that is the situation related to the different modes of operation. One of the important things that needs to be done in a system like this is to maintain the state of charge. And I think that I have already explained and shown you this diagram that illustrates the situation with the state of charge of the vehicle. I'll show the diagram next. But the target state of charge nominally that Toyota wishes to achieve is 60%. What's going to happen then is that you're going to have a state of charge management system that is going to try to accomplish this. First of all, you will never operate in very low and very high state of charge regions, because this is not good for the health of the battery. You are then going to have some yellow region where it is not especially damaging to be there, but you try to avoid entering that region because you wish to be, the majority of the time, you wish to be inside this control region. And you have a target state of charge that, on average, you wish to maintain. Now, it turns out that the voltage state of charge characteristic of a nickel metal hydride cell is relatively flat. You know, I know that some of you work on battery-related research at CAR, and you have looked at a lot of voltage state of charge characteristics for NMC, LMO, LFP, LTO, different kinds of lithium cells with different chemistries. And those voltage characteristics versus state of charge. So here's the voltage, here is the state of charge. Let's say this is 0, let's say this is 1. There is a clear characteristic, which there is a minimum voltage and a maximum voltage. That's a fact. You cannot deviate from that. Obviously, you're going to be, you reach the minimum voltage, that's automatically associated with 0% state of charge. And of course, the maximum voltage, which is typically important when you charge, is associated with 100% state of charge. So what happens is that you get from 1 to 0 in different ways. Every cell tends to have a fairly rapid drop, then it settles down, and then it has a need that takes you down to 0. Okay. Let's say that red is some kind of a lithium chemistry. And even within lithium chemistries, there are substantial differences. For example, iron phosphate cells have a flatter voltage state of charge characteristic than NMC cells, for example. If I look now at the nickel metal hydride chemistry, the nickel metal hydride chemistry is very flat. The slope here in this central part is very shallow, which makes it actually very difficult to estimate the state of charge, because the voltage doesn't change in a dramatic way. And so state of charge estimation is difficult in nickel metal hydride batteries. So let me be conservative and say that in a nickel metal hydride battery, if I have done a good job of positioning, of developing a state of charge algorithm, I am probably within plus or minus 10% of the truth. That's a big error margin. And plus or minus 10% could move you into the yellow area, and that's not good, because another 10% error and then you're in the red area. So the fact of the matter is that if you were to actually take a look at what a realistic, see, this picture is not to scale. I am going to try to give you an image to scale from 0 to 1 of the state of charge colors, so to speak, of what really happens in a Toyota Prius. So first of all, we set the target at 60%, okay? That's the target. Then we agree that there is red at the top and at the bottom. Now, we actually, in the early days, Professor Guisenek was the happy owner of a Toyota Prius early on. I don't remember whether he bought one in 2004 or shortly thereafter, but he's been driving Toyota Priuses since the Toyota Hybrid System 2 came out. And he was kind enough, he's also an engineer and a nerd like some of us are, and so we immediately developed access through the OBD port to information from the Toyota control system. It took a little while, but there was a group of interested people, owners of Toyota Priuses, who figured out ways to somehow crack the CAN code. And so you could find online, 15 years ago, okay, you could find online the CAN codes for different signals. So it became relatively easy to actually, through the OBD port, acquire data and see what really happened. So if you have current data over a period of operation, you collect that data, you put it in your computer, and you do a Coulomb counting, a numerical integration, you can actually see the deviation in state of charge that you really have in practice. And so here is what happens. I'm going to go to the green. From extensive operation of a real Toyota Prius, trying hard to charge it and discharge it. By the way, there is a display. I remember driving it over long distances, and my game was to try to, get the state of charge as high as it would go, or it gives you, there is a bar graph that tells you how much energy you have recovered, and so you try to see, can I recover, how many kilowatt hours can I recover from braking regeneration, okay? So you can play all these games. But after a pretty extensive set of experiments, what we basically concluded that to stretch this from 0.6 to 0.7 to 0.7 and to 0.5, in other words, plus or minus 10%, using 20% of the total energy available in the battery was the limit of what you saw. And so you see that this Toyota diagram on the right-hand side is actually not to scale. It tells you the truth in the sense that there is a preferred region, some region where you can be but would like to avoid, and some forbidden region. That's true. But the size of these regions is actually quite different. And what happens, the reason for that is that this 20% of the state of charge region that you use, because of your uncertainty in the state of charge estimation, could be anywhere in here. The 0.5 to 0.7 is nominal. It could be 0.4 to 0.6. It could be 0.5 to 0.8. And because you really don't know where the state of charge is with sufficient accuracy. Therefore, the choice that Toyota made was to design a battery pack that was substantially oversized. Because if you're only using 20% of the state of charge, you really have 5 times the kilowatt hours that you really use. Now, I'll grant you that maybe the top 10% and the bottom 10% you would never use anyway, so instead of 5 times, you have 4 times the capacity you can use. But that was a safe condition, because by having a larger battery pack, what happens to the C rates? They go down. C rate is dependent on capacity, right? So your C rates were relatively were lower, or rather you could afford higher C rates or higher currents, right, without incurring extremely high C rates. And I remember many years ago doing some work in exploring, this is work that Professor Wizenek did actually many years ago. We were exploring the use of these nickel metal hydride cells for other industrial applications, and we were looking at very deep discharge rates, so more greater depths of discharge. And while a nickel metal hydride battery used in this mode with a shallow depth of discharge, only about 20% of the total capacity, will last literally forever. If you take the same cell and increase the depth of discharge and use, for example, 50% of its capacity instead of 20%, it will age much more rapidly. So these are all considerations that are very important and that need to be made in thinking about how to manage the operation of a hybrid electric vehicle. So this lecture was a little bit shorter than usual, which makes up for some of the times when I have gone overboard. So this time Chitra doesn't have to run out to her next class. I wonder if there are any questions. We have plenty of time. I'm okay with stopping a few minutes early, but there is a question in the back.
How do you have to change the regenerative braking strategy if the SSE is too high?
Yeah.
So if you're going down like a mountain for a long time.
Excellent question. So the question is, do you have to change the regenerative braking if you could achieve too high or too low states of charge? That's another reason why having a relatively narrow band of SOC is an acceptable, is a desirable thing, because if you now have, as you say, you're coming down a mountain, right? Could cause you to exceed the state of charge. So in the Toyota Prius, there is a state of charge control that will not let you go above a certain point. So unfortunately, if you're literally coming down from Pikes Peak and going down to as low as you can go, which would be a delta altitude of maybe 2,000 meters or something like that, right? If you do that, at some point, the battery will not accept regenerative braking anymore. And in fact, the Toyota Hybrid System 2 has the knob, the shifting knob, allows you to go into a compression braking mode. So you can yourself choose to have more engine compression braking, which is something that you would do if you're driving in the mountains, for example. But if you don't do it manually, in any event, when you reach some upper state of charge limit, the battery will stop accepting charge. So the battery management system will handle that situation. It's just too bad because you have all this great potential energy you had at the top of the hill, and you're not going to be able to recover all of it. This is, by the way, where having a geographical information system of some kind, right? You are climbing Pikes Peak, and then you're going to come back down the other side, okay? If you know where you are, you could actually purposely use as much of the electric power as you can climbing up the mountain, because you know that you'll get it back. So you would be able to, first, upon climbing, you would reach the lowest possible allowable state of charge, because you know you're going to get it back later. So that's where information about the future is actually very useful. It allows you to optimize things. If you're completely ignorant and blind and don't know that you're about to go up and down a mountain, you will not have as much overall fuel economy as if you knew that piece of information. Good question. Yes, sir.
Yes, sir. How can you afford to oversize the battery pack in a situation like competition when the weight of the vehicle is very important?
Right. So, a good question. So the question is, how do you deal with this oversizing of the battery if you're dealing with a competition? And you can, you know that, for example, in Formula One, there have been hybrid electric kinetic energy recovery systems for many years now. So the answer is you cannot. But I can tell you that what Formula One does with hybrids could not have been done in the world of nickel metal hydride batteries. okay? And I don't know what the sporting regulations are with respect to changing the battery pack. So one of the big differences is that Toyota gives you, the customer, a warranty, 5 years, 100,000 miles powertrain warranty, or 7 years with 150,000 miles. That means that Toyota wants that battery to last at least 7 years. In fact, for customer relations perspective, they want it to last 10 years, which it did. Okay. If you are in a Formula One race, okay, or racing situation, at most you'll use it 1 year, because every season the vehicle is different. And then the question I have, and I don't know what the rules say, you could replace the battery a few times during the course of the season, right? So how many engines can they use in Formula One? 5, 3, what's the number? I don't know. So presumably, I don't know what the rules with replacing the battery are, but in a competitive situation, you can afford to be much more aggressive, and so that range over which you use the battery, yeah, you'll stretch it out a little bit. Now, I would say that conservatively, with a lithium battery pack, you could probably use 50% of the available nominal capacity. So you're only oversizing by a factor of 2 instead of a factor of 5. But if you're in Formula One, maybe they figured out ways to use 60, 70% of it, okay? But it doesn't have to have as long a life, so you don't care as much. Good question. Chitra.
When we were talking about different configuration while like starting out or reverse, you said that MG1 is not doing anything, it's just freely rotating. But we don't have a clutch, and there is a kinematic relationship between the torques. So it's just, I can't picture in my head what's exactly happening, because we have a kinematic relation which relates the torque of the sun gear to the torque of the ring gear. And you have because it's rotating as well. So there is a power which is associated with MG1. How is that happening?
Yeah, so good. Chitra is asking a question essentially about this diagram here.
Yeah.
So what happens is this situation is that if I am doing a light electric vehicle launch, I am actually providing positive power request to MG2. I do that quite simply through my supervisory controller. I say, hey, inverter, give me so much current to the electric motor that will produce torque. When that happens, one, the engine is stopped. And so accept the fact that the carrier is stationary, okay? The engine is stopped, that's not going anywhere. So now, when and the reason it's not moving is because it's true that it is connected to the ring gear, but the ring gear is powering the wheels and the vehicle is moving. So when that is happening, the engine will not start and will not move, because all the power is going to the wheels and you can move the vehicle forward. Now, if you accept the fact that the carrier is at 0 speed here, then what's going to happen, somewhere I have an equation, there you go, that was the one. What's going to happen now is that with omega carrier being equal to 0, in that condition, you're going to have omega ring is equal to minus ns over nr times omega s. By the way, you are doing the class a favor, because this type of thinking could appear in the midterm exam. It's entirely possible, okay, that you would have to do this type of analysis in your head. So it's a very good question. I'm glad that we had a little time to chat. So what happens now is that the sun gear is rotating at minus nr over ns times the ring gear. The ring gear is related to the speed of the vehicle, okay? What do you think is larger, nr or ns? NR, the ring is outside, it's got more teeth, okay? So this number is greater than 1, right? Okay. So what you're going to have now is that the sun is, if you don't have any brakes or any clutches, okay, as you recognize, the sun has to rotate in opposite direction at a speed that is somewhat greater than the ring gear speed. by the ratio NR over NS. Let's go back and look at this diagram. So you'll notice here that this number is this big and this number is that big. So NR over NS greater than 1, okay? And so you see that in this case, MG1, the rotor of that machine has to spin, okay, backwards. Now, if I electrically do not provide any power to the stator of that machine, so my stator is absolutely turned off, what I am doing is I am spinning the rotor of an electric machine, which is essentially a dead body, is a piece of iron with some magnets in it that is just rotating in the opposite direction. Until I applied an electromagnetic field to it, nothing happens to it. It's just spinning backwards. That's all it's doing. Yes, I have some small friction losses, but they're really small, okay? So that's what happens in that case. So let's go to the next step. The next step now is that I am going to now start the engine. And I am going to start the engine, and once I fire it up and the engine begins to rotate, I am now going to change omega c. Omega c is now no longer 0, so this entire curve shifts up. This is my new reference point. Now, the ratio between the mg2 and mg1 is different. Agree? Let's go see why it's different. It's different because omega c is not equal to 0. So now, whereas before the sun was rotating at nr over ns times the ring speed, now the sun is rotating at a speed that has to take into account all three speeds and these ratios as well. So if you wanted to, you could calculate omega sun as a function of omega carrier and omega ring. You can do that, okay? I'm not going to do the arithmetic right now, but you can do that. And so what happens is this picture shows you what the result is. If I didn't power the sun, the MG1, if I didn't do anything to it, so in other words, if I didn't have that green arrow, it would still spin, but instead of spinning backwards, it just so happens that it would spin forward. There would be a reversal in the direction of rotation. But I also power it, and I power it to make it operate as a generator. So that means that some of the power that is provided by the engine is going to actually flow into MG1, and that MG1 electric power is available on the electric bus. You can charge the battery, or you can help the MG2. Does that make sense?
Just a little bit addition. So we have like torque, which is also related kinematically, right? We have like ring torque at sun gear, which is ns over ns by nr into carrier. So that torque is just a reaction torque that the shaft takes, or what is the torque?
So the torques, very good point. In this case, what's going to happen is, you said exactly the right word, so you're asking a question, but you knew the answer already. It's a reaction torque. Whenever you use an electric machine as a generator, that electric machine produces electricity, but you have to do some work to produce that electricity. That work is manifested in the form of a reaction torque. Think about it this way. I don't know if you've ever done this, but if you go to COSI, back in the days where my kids were little and I used to go to COSI, this is like a science museum for those who don't know what COSI is. There was a bicycle connected to a generator to a light bulb, okay? Well, you can pedal the bicycle, and it takes a certain amount of work, or you can pedal the bicycle connected to a generator to light up a light bulb. You have to do more work. There is a reaction torque in the generator the moment you start producing electricity to light up the light bulb. So there is a reaction torque here in the MG1, which is in the sun, and that's going to be in the opposite direction. I'll write minus, whereas I have plus IC engine torque at the carrier, and plus electric machine torque at the ring. And those relationships are back in the previous lecture when I talked about planetary gears. So that is exactly the kind of analysis you need to understand, and you did homework assignment problems related to that.
The same question, like, do we disconnect the MG1 when we are rotating it backward, because otherwise there will be back EMF generated, because the conductors are still there, and the magnetic field is rotating because of the rotor, because there are magnets on the rotor. So back EMF will be generated, that will produce a torque.
A back EMF is generated when the stator is active. If the coil is, so you basically, if you have the field off, okay, the machine is just idling. It doesn't do, you have a reaction torque, you have a little bit of reaction torque caused by friction and windage, but you're not going to have a back EMF if the machine is not powered. It's essentially, think about it this way, the electrical part of MG1 is disconnected from any power supply. So let me put it to you, I wish that I could sort of show you this, but if I had a motor and I say spin the shaft, when everything is disconnected, the wires are all open, you can spin the shaft.
By rotating it, there won't be anything, no, apart from the pressure resistance, there won't be resistance from windage.
If it's electrically disconnected, no, it's essentially just idling and you have the mechanical connections, the mechanical and aerodynamic resistance. Okay, well, it turns out that we ended up using the lecture time anyways, so good. Thank you so much, and I will see you on Friday when we begin a new chapter and we'll talk about optimization, okay? See you in a couple of days.